All right, then our next speaker is Yunchao Liu here from Berkeley University, who will tell us about learning shallow quantum circuits and quantum states. The stage is yours.
Thanks. Hello, everyone. It's my pleasure to talk about learning shallow quantum circuits and quantum states prepared by shallow circuits in polynomial time. This is based on this paper and a new paper with Zeph. So let me start by just saying that here are two fundamental problems in quantum complexity theory and quantum learning theory. So here's the first problem. Given access to an unknown constant depth quantum circuit U, as shown in the figure, we want to learn a constant depth quantum circuit that is close to U, let's say in diamond distance. So the learning algorithm can access U and want to figure out a description for U. Here's the second problem, which is a bit different. So now we are given copies of an unknown quantum state psi, which is prepared by some unknown constant depth circuit U, as shown in this second picture. And now the goal is to learn a constant depth quantum circuit that prepares psi. So the learning algorithm can just measure copies of psi and then try to figure out a description of psi. So in this talk, we will give polynomial time algorithms for both problems. And this algorithm still works when the depth of U increases to polylog n at the cost of quasi-polynomial running time. And throughout this talk, I will assume that the system is defined on a finite-dimensional lattice, and I will address more general geometry at the end. So next, I will discuss some motivation in the context of this workshop. So one way to think about NISQ computation is that they can be modeled as shallow quantum circuits. So shallow quantum circuits are very simple, but still they are interesting because they can generate probability distributions that are classically hard. And this is really the complexity foundation for the hope of quantum advantage. And this has motivated a lot of NISQ algorithms. And if we distill the key idea behind these algorithms, it is try to discover a shallow quantum circuit as a solution to an interesting problem. Assume such a solution exists. And this, indeed, can be formulated as a learning problem. So the main challenge in this direction is to develop efficient learning algorithms to find these interesting circuits. And in this context, this talk is just two new learning algorithms that probably work in simple settings. And of course, an exciting future direction is to study whether this can provide new primitives for new NISQ algorithms. So now I'll briefly discuss the key challenge in this problem. So all of the algorithms we will see today follows from a two-step procedure. The first step is to learn local observables. So here I should say that this is very easy to do, because if we want to learn local observables, we can just do local tomography. But of course, the modern approach is to use classical shadows. And moreover, we also know that because the underlying quantum circuit is shallow, actually local observables suffices information theoretically to reconstruct the circuit. So the challenge here is really all about step 2, which is to efficiently reconstruct a quantum circuit from learned local observables. And hopefully I will convince you in a second that this is a highly non-trivial problem. And the goal of this talk is to demonstrate new and simple techniques to do this. So let's start with the first problem, learning shallow quantum circuits. This is based on this paper with Robert, Michael, Isaac, Anurag, Zeph, and Jared. So to recap, we just have access to this unknown unitary U, and we want to learn a shallow quantum circuit to implement U. So here, the learning algorithm actually only need very simple access, which is single qubit random input-output samples, which is random single qubit stabilizer states and measurement in a random Pauli basis. This is also known as the classical shadows for quantum circuits. So next, I will discuss how to achieve this result. Polynomial time algorithm for learning shallow quantum circuits from random input-output samples. So let me start with a very basic picture. The first thing to say about this picture is that now I have switched the quantum circuit from bottom to top instead of left to right. Hope that's clear. Okay, so if we consider a small region A, let's say it's defined on a lattice. Here I'm only showing 1D, but we can imagine this happens in a higher dimension as well. And then we can see that there is this light cone structure where each input qubit in A only affects a small number of output qubits, which are in the light cone of A. The light cone is defined as this blue circuit, which is visually very clear. So here is a naive thought. If somehow we can undo these blue gates, we can somehow just remove them, then life would be very easy because we simply have a smaller circuit which acts on smaller number of qubits, because now the action on A is just the identity, and everything else is still a shallow circuit. But of course, we cannot do that because we don't know what are the gates in the blue region. So here is a basic idea of something we can do. The basic idea is that since we don't know what are the blue gates, notice that it's only a small piece. So maybe we can try to guess a small circuit, the green circuit, to disentangle the region A. So that the idea is that we try to guess some gates in the green piece and then apply it, and then try to see if the qubits in A was indeed disentangled. So let's try to say it in a slightly more formal way. So this basic idea has a name. We call it local inversion. So local inversion is just guess a small circuit to disentangle a small region. So how do we actually do this? Well, it's very simple, right? Because the green circuit is very small. So we can just enumerate all small circuits and apply them one by one. And for each of them, we can test if the qubits in A was indeed disentangled. But of course, there is an issue. The key issue is that the small circuit, the green circuit that we apply, could be different from the actual light cone, which is the blue. So even though we can disentangle the region A by applying the green circuit, what we applied, the green circuit, is not necessarily actually canceling with all of the gates in the blue. So it could just be some other circuit that happens to disentangle A. In other words, instead of removing gates from the unknown circuit that we're trying to learn, we are actually adding more gates. And this really creates a mess on the remaining qubits, even though we can sort of remove the qubits in A. So next, I will just present the key idea to avoid this issue. Okay, so the key idea is a three-step procedure, which we call disentangle, swap, and undo. And I will just show you how it works. And our starting point is the same picture as what you just saw, except that here is more abstract. So we have this unknown shallow circuit U in red, and we want to apply a local inversion, which is this small circuit V1. And after we apply it, it disentangles this qubit A1 into a wire, simply the identity operation. But the problem here, of course, is that the remaining circuit U prime could be a lot more complicated. So our idea is to introduce a new ancillary qubit, swap with A1, and undo V1. Okay, so let's see how it works. The first step is very easy. Just add a new wire. It's not doing anything. The second step is also very easy. Swap, which is also not doing anything. Just swap A1 and B1. And the third step is also very easy. We just undo V1 by applying V1 dagger. Now we are done. That's the key idea. Okay, so the interesting thing about this picture is that we almost didn't do anything. Because indeed, if we didn't have this swap in the middle, then all we did was V1 and V1 dagger, which is nothing. But we have this swap. So what it does is that from the perspective of the last picture, it feels like the identity of A1 and B1 has been changed. In other words, this last picture is actually equivalent to this new picture. We still have the same quantum circuit, except that somehow the first input wire is now swapped into B1 instead of A1. And now A1 is simply doing nothing. Okay, so why is this helpful at all? So if we want to summarize what's going on in this entire procedure, this is what's going on. So we basically have learned a small circuit W1. It acts on top of U1. It acts on top of U together with some new wire. The thing is that after we apply U1 to this system with this new ancilla, it is equivalent to the right-hand side picture, which is the same circuit U, except that somehow it achieves the effect of swapping an input wire. So the key observation here is that the system is not disturbed. If we examine the right-hand side picture and look at it from the top, it feels like nothing has happened. And therefore, we can now repeat this procedure. Because at the beginning, we were worried about creating a mess. But now this right-hand side picture is not a mess. It's very clean. OK, so now comes the big claim. The claim is that this idea indeed works. And using this idea, we can learn the description of a 2n-qubit circuit, W, that somehow satisfies this property. It implements the unitary U-dagger tensor U. OK, so our goal at the beginning was to learn to implement U, but now we can implement U-dagger tensor U together. But of course, that's fine. We just get something extra. OK, so how do we get this circuit? Here is how it works. We just start from the same picture. So at the bottom is what we have done. We have applied this small circuit W1 on top of the system that sort of swaps an input wire. But now, because the system is not disturbed, we can do this everywhere. We can do the same operation at the bottom, but now repeat this on every qubit. And what it does is it just swaps everything at the input, which is this. OK, so maybe this looks not very nice. So why don't we apply a final big swap on top again to achieve this? OK, so this is somehow what we get after all these things are done. And to summarize what we have done, we have exactly learned a 2n-qubit circuit W on top of everything, including the unknown circuit U and n extra wires. But somehow, it achieves the effect of moving U from left to right. And of course, if we examine this picture, we just get that W is exactly equal to U-dagger tensor U. And therefore, our problem is solved. If we distill the key idea of how this worked, it's really trying to disentangle a local region without disturbing the system. Yeah, question.
W is a deep circuit now, no?
Great question. That's exactly what I'm going to talk about next.
Yeah, that's my question.
OK. So now you may be wondering, well, if you really follow what I did earlier, it feels like this W thing is quite deep, right? Because it feels like sequential, and also it has a lot of ancilla. So next, I'm just going to tell you how to reconstruct the circuit in low depths by showing an example in 2 dimensions. So the first, I just want to say that this picture is very nice. Because it has 3 colors, right? It has red and green and blue. But if you look at each color, right? If you look at each green colored region, every green piece is sort of far away from every other green piece. And the same is true also for the red and blue. And somehow this is really important. OK, so let's see how to use this picture to reconstruct the circuit in low depths, which happens in 3 layers, exactly corresponding to the color. OK, so the first thing is that we will try to do this in parallel for all green regions. Step 1 is to apply local inversion operator for each green color. Notice that each green region is far away from every other green region. And therefore, this local inversion can happen all in parallel at the same time because they does not interfere with each other. That's fine. So the second step is to swap each of the entire green region with new ancilla wires. So now you may be wondering, OK, so you want to introduce ancilla, which can be like far away, right? So how do you connect the system and the ancilla? Maybe this swap is kind of long range. So now we need to use a new trick. So actually, the reconstructed system looks like this. So originally, we just have these black qubits. But now the reconstructed system has these new red qubits, which is ancilla qubits. And each qubit has its own ancilla qubit nearby that is connected to it. So actually, if we reconstruct the system in this way, all of the swap operations are local. And of course, the final thing is undo. And then we just do the same for red and blue. And you can see that this is indeed in low depths. And of course, there's a final global swap, which is also low depths. Okay, so that's it. Okay, so I will talk about something next, and you will probably not believe me. So it turns out that we have presented this very simple algorithm, but there is an even simpler way to think about this. So now the key observation is that if we really look at step 1, 2, 3, we do them sequentially, right? But actually, we can combine these 3 steps together into one step. And this operation is somehow equivalent to this following operator, which is U dagger SIU, where U is the unknown circuit and S is the swap. So I will not show you why this is true. It's not very hard to see this. But instead, I will do a sanity check. Because we can see that previously in step 1, 2, 3, we are just doing local operations. So it must be the case that if I claim what I claim here is true, it must be the case that this operator U dagger SIU is also a local operator. Well, that's very easy to see, right? Because U dagger SIU looks like this. And everything cancels out except the blue region. So indeed, U dagger SIU is a local operator. So now I claim that there is a simpler algorithm. We can just directly learn these operators, U dagger SIU, without going through the local inversion. And then we can directly combine them into a circuit that implements the same thing, U tensor U dagger. Okay, so I will not explain how to learn these local operators. Hopefully, I can convince you that they are not hard to do. But I will comment on this last sentence. Because we have actually seen how it works. It's just this one-line proof, which is an identity that holds for any unitary. You can decompose any U tensor U dagger in this fashion. And we exactly have seen how this works because it looks like the same thing, right? You have this global swap, and then you have a sequence of local operators. But what is interesting about this identity is that it gives us something even better, which is actually this algorithm also directly applies to learn any unitary that maps a local operator to a local operator. And this family of unitary in physics is called quantum cellular automata. It's more general than shallow quantum circuits. Okay, so that's all I want to say for part 1. Any questions? Yeah.
So when your original unitary had depth B, you now also have a unitary with depth B, or just a shallow?
Oh yeah, so the learned unitary, which is this procedure, it roughly have depths like 2 times k times d, where k is the lattice dimension, which is constant times d. Yeah.
Okay, maybe later.
Is there some reason why you need 2n qubits? Like, is it possible to do this with just using n+1 qubits?
Great question. Actually, I will answer that very specifically at the end. It's a deep question.
So I'm trying to think about like the requirement of finite dimension.
Yes.
Does that come from like the colorability of the regions such that you can parallelize everything within constant dimension?
Yeah, as I commented at the beginning, I will address more general geometry at the end. But the short answer is that this actually works for any kind of geometry. Yeah.
Is it immediate to see that if you have a circuit for U, that U tensor U dagger, then you can turn it into a circuit to just U? Know that?
Oh yeah, because you can simply ignore the other half, right? You can put your desired input on the half corresponds to U and get your desired output. You don't need to care about what happens on the other half.
Then it creates entanglement between registers. That's not the same effect as U.
Well, okay. So the unitary we apply is not entangled, even though the circuit can be entangled. The unitary we apply is equal to U tensor U dagger. There's no entanglement there. But somehow we implement this not-entangled procedure, potentially using an entangled circuit. That's the magic. Yeah.
So this algorithm is sequential. Is it robust against statistical errors? For example, you assume that the estimating the local observable is for free.
Yeah.
But if suppose have an epsilon error for the initial step, and then you build the later steps of the algorithm on top of this incorrect information,
Yeah.
how does the error propagates?
Yeah, the error just propagates additively. Like, so you want to make sure every step has error like epsilon over n or something, so that it builds up additively.
But is that too good to be true? No, because not only like a size is one thing, but they also spread. So maybe your intermediate steps, U might not be exactly the same U, but the perturbed, not only the content, but the geometry. That's the case?
Yeah, well, we can actually literally examine this equation. This equation is just a product of a bunch of local operators. If we can learn each local operator within epsilon error, then the whole thing has epsilon times n error.
Yeah, but when you perform measurement of the second steps, that measurement will not only have an epsilon
Oh,
error,
I see.
but it's relying on the previous knowledge, so it will have a more error. No?
Yeah, sorry. So I should say that all of the procedure that I described earlier is just a thought experiment. Actually, what we really do is just a classical post-processing of the classical shadows. That's the only thing we do.
The measurement is all done at the beginning.
Yes. Okay. So let me continue to the second part, learning quantum states prepared by shallow circuits. This is upcoming work with Zeph, and there's also a related upcoming work of Han-Soo Kim, Isa Kim, and Daniel Renard, which has a different approach. Okay, so now we want to have this consider this different problem. So now the goal is that we want to learn a shallow quantum circuit to prepare an unknown state psi. So here I really need to clarify that this is a very different problem, because we only have access to the quantum state psi, not the quantum circuit that prepares it. So the learning algorithm only just get a bunch of copies and measure it. And of course, what we literally do is just the classical shadows. And next, I will discuss this algorithm for learning quantum states prepared by shallow circuits from random measurement samples. So this will be a very different algorithm.
But is this a strictly stronger result?
I would say it's incomparable, because the first problem, it has a stronger requirement. You have to reconstruct a unitary that is close in diamond distance to the unknown circuit. Here, you only require that it prepares one state. Yeah. Okay, so this new algorithm will be very different, but somehow it shares some similar spirits as what we just saw. So here's how it works. The basic idea is the same, which is local inversion. But of course, here local inversion means something different, which is we have this quantum state psi, and what we will do is try to guess this small circuit V1, such that if we apply it to the psi, it inverts a small region to the 0 state. And what to do next? Well, there is some exactly the similar kind of issues that we have seen earlier, which that if we continue working on this new state phi, that could be a much more complicated state. So we want to somehow get around this issue. Okay, so here's the key idea, which is just local inversion and undo. So previously, we have this kind of fancy technique of doing the swap, but here we're not even doing anything fancy. We're just somehow just local inversion, undo, and somehow that works. Okay, so step 1 is to apply a local inversion V to invert a small region A, and what we get is the tensor product of 0 on A and some complicated state elsewhere. Step 2 is to replace the qubits in A with fresh qubits in the state 0. And of course, this is not doing anything because the qubits in A were already in the 0 state. But I'm just including this step for convenience later. And step 3 is just to undo the local inversion, but by applying V-dagger. Okay, so why is this any useful? So here's the first observation, which is that we have done a bunch of things, but at the end, the state psi didn't change at all. Well, this is a completely trivial observation because what we did is just V and V-dagger. So here's the second observation, which is that if we really examine what we have done, it turns out that we can say that we have learned a small part of the state. So how is that? Well, let's say we examine an even smaller region inside of A. Let's say the region A0. Then we can sort of already say that we have learned a circuit for the reduced density matrix on A0. Because if we just want to prepare A0, all we need is to implement the backward light cone, which is the small green circuit, acting on the fresh qubits, which is 0. And then we apply this small green circuit and trace out some of the unnecessary qubits, and then we get the reduced density matrix on A0. But of course, this observation is also trivial, because if we just want to learn a small part of the underlying quantum state psi, we can just do that directly. So really the non-trivial thing is to combine both observations, which is this. So somehow by doing this V and V dagger, we are able to say that we have reconstructed a small part of the state without changing the state at all. So any question about this comment? Okay. So this is somehow saying something interesting, right? Because it says that somehow we can do something good that doesn't change anything. And if you can do something good that doesn't change anything, why not repeat? So next, we are just going to repeat. So here's the first repetition, right? We have done this just 1, 2, 3, 4. And indeed, we have reconstructed part of state, which is the green piece. So if we start from all 0 at the fresh qubit, we apply this green-shaped circuit. And then we can get some reduced density matrix of the state psi.
So all this refreshing part should be understood as the doing measurement and replace.
Yes. Yeah. Okay, but are we done yet? Well, of course we have not done, right? Because we are missing some stuff. So the thing we are missing is that, of course, there are something outside of the green, in particular the red circles, which we cannot say that we can reconstruct at this point. Right? So what do we do with these red regions? Well, we don't have any idea except to further repeat. Because, again, the state completely did not change. So we can just repeat however we want. Maybe we can add another layer and see what happens. So here's another layer. You can see that it quickly gets a lot more complicated. So now, does this picture work? Well, there is a potential issue, which is that now we have added more stuff in a new layer. And this new layer could mess up with what we had earlier. Because I just want to say that it's not so obvious what's going on in this new picture, because we have done new stuff on top, which could actually change a lot of things. But now I'm going to present a big claim, which is this actually works. We have solved the problem, and we already reconstructed circuit for preparing the unknown state psi. Okay, so how does this work? This brings the final key idea, which is that why don't we try to be very brave and reconstruct the state all at once, just by looking at the backward light cone of every qubit? Can that work? Okay, so something is going to happen. Don't close your eyes. This is what happens. Okay, let me play it again. Okay, so this is what happens if we try to reconstruct the entire output state at once by tracing the backward light cone of all wires at the same time. Somehow, we can just, this is a very visual, right? We can just imagine we start from the top and we start spreading green color downwards. But some of the spreading already stops at the top layer of fresh qubits. But some of the spreading continues. But nevertheless, it stops entirely at the bottom layer of fresh qubits. So the key reason that this works is because the backward light cone of the entire output stops entirely at fresh qubits. And now we have the circuit. So what exactly is the circuit? And how exactly do we prepare the state psi? Well, this is exactly what we do. You can somehow see that I'm doing this on purpose by showing the picture in this direction, right? Because this is exactly how we prepare the state psi. The interesting thing about this picture is that there are some extra qubits, the red qubits, that we can sort of use temporarily and then throw away. So these are the ancillary qubits that we need very naturally for this procedure to work. Okay, so at this point, you must feel that there must be something non-trivial going on here. Because this is a very sort of magical argument, it seems that it must rely on some careful geometric arrangement. Because if you just arrange these things arbitrarily, it probably doesn't work. And indeed, the final thing I'm going to talk about is how to have this geometric arrangement to make this work in general. Yeah.
I just was wondering, so you mentioned that those red kind of correspond to some ancillary.
Yes. Yeah.
It looks like you can just reuse, right? So like in total, you could run the whole circuit without any ancillary.
That's a great observation. Yes, that's true.
Okay, cool.
Can you guarantee that these red ones are actually entangled and disentangled after the circuit?
That somehow that must be guaranteed by this argument, and somehow you can also see it by examining it very closely. It's really sort of magical that these red qubits are naturally disentangled as you go with the circuit. Okay, so now I will just discuss what's the underlying principle for this geometric arrangement to work. So we can divide the lattice into subsets, which are the red stuff here. And there are two key principles that's going on here. The first principle is that subsets in the same layer are sufficiently non-overlapping. For example, in the both top and bottom layer, they are both sort of far away from each other because now we can do the local inversion in parallel. And the second principle is that somehow subsets in different layers are sufficiently overlapping, which makes this light cone argument work. And really, the key question is, how do we do this in general? Because in 1D, this looks very simple, but in higher dimension, it could get a lot more complicated. Okay, so I will just conclude by sketching how it works in 2D. Well, we have the same picture, which is very nice. So we have this picture, and we can divide it into 3 layers: red, green, and blue. Of course, this picture satisfies property 1, which is that if we examine each layer, they are sort of sufficiently non-overlapping. But of course, property 2 is completely missing because different layers are also non-overlapping. But look at this picture, we realize that there is still some slack in each layer. So actually, now the construction is that maybe you can just grow each of these small pieces to make them a little bit bigger. So something is about to happen. It goes like this. Right, so now we can satisfy both property 1 and 2 at the same time. We still have property 1 because they are still, in each layer, they are still non-overlapping, but now there is sufficient overlap between different layers because we just made them bigger. Okay, so now we are completely done with the argument. Yeah. Yes. Because you need to start with this, you can construct this color on the left-hand side. In k dimension, you need k plus 1 colors. Okay, so let me just conclude this part by a physics comment. So in physics, there's something called phases of matter. And the trivial phase is defined as quantum states prepared by constant depth circuits acting on a finite dimensional lattice. So what I just presented is a proof that quantum states in the trivial phase can be learned efficiently. And this directly gives a property testing argument. So given an arbitrary state, whether in the trivial phase or not, we can sort of efficiently test whether it is in the trivial phase, in other words, has low circuit complexity, or in the topological phase, in other words, has high circuit complexity. That's the simple corollary. Okay, yeah.
Your construction works only when you have the ability to locally disentangle qubits.
Yes.
So can you actually locally disentangle qubits even the topological phase?
Okay, so The idea is that if I give you a topologically ordered states, you cannot always locally disentangle the state if you run the algorithm, and then you will know that it's not a trivial state.
Well, you could factorize all the product states out of topological qubit, except for the one last non-local polynomial. So can you use this to decompose generic topological circuit as a non-trivial, non-universal component tensor product component? Isn't that already implied?
I'm not sure I exactly get what you're saying, but maybe you're trying to say that maybe we can learn some kind of topological order states in this way, which I think is possible. Here, I'm just saying that we can distinguish between low circuit complexity and high circuit complexity using exactly this algorithm.
Yeah, maybe I can clarify this because here you need a uniform upper bound on the circuit depth that can disentangle a given region. So, like, no matter how large the region is, this disentangling circuit has to be like its depth has to be like bounded by some constant. And for topological phases, you can't have this. So this condition is not satisfied for topological phases. So like, let's say you have like an L by L region, you want to disentangle that. You need like circuit depths of at least like L. But here, like, it's just a constant.
But if you want to disentangle this one qubit out of one code, can't you use just like 3x3 qubit, the 3x3 unitary of the depth maybe 3 to disentangle one qubit in the large Tor code?
But if the disentangling circuit is too deep, then like it'll spread too much. So you won't have this nice property that's satisfied here.
Maybe let's chat afterward.
Yeah, great question. So okay, so I will just conclude by having some final discussion. So one question that came up earlier is, what about more general geometry beyond the lattice? So for the first algorithm, learning shallow quantum circuits, it just works for arbitrary geometry or even unknown geometry. Just because this simple decomposition formula, this one-line proof, it just always works. And for the second algorithm, learning quantum states, we sort of really need this intricate covering scheme defined on some geometry. So as long as we have this covering, it works. But we only constructed this covering scheme for lattices. So for what kind of geometry this works, we don't know yet. The other question that came up is, okay, what about ancilla qubits? We can very clearly see that in both algorithms, using ancilla qubits is very essential. So the question is it possible to reconstruct the circuit without using any ancilla qubits? So this is open, and I believe that it's hard in general, but we can do something. So it turns out that in this first paper, we also have an algorithm just for learning quantum states in 2D that doesn't use any ancilla qubit, assuming a finite gate set. And the key idea is to observe that to learn this state, it suffices to solve a one-dimensional constraint satisfaction problem, which is efficient. And maybe it also works for learning a quantum circuit in 2D. It's plausible we didn't do it. Yeah, so that's what we know. Okay, so let me conclude the entire talk by giving some brief outlook towards useful quantum advantage, learning shallow quantum circuits in NISQ algorithms. So what we have presented is two new learning algorithms based on local inversion that works in simple, clean settings. And they are very different from gradient descent, which is what people do in practice. And the exciting direction is, can this be the basis of efficient learning algorithms in more general settings that solves interesting problems in NISQ? And for this, we really need to deal with a lot more practical issues, such as noise. So this talk is really, hopefully, the beginning of things. Thanks.
Thank you very much, Yunchao, for the very nice and colorful talk. Are there more questions?
You said your first algorithm works for any geometry, but what if there's no geometry at all? If it's just all to all, what happens then?
Yeah. So maybe you're asking, what if you don't have any prior knowledge about the geometry?
Yeah.
The thing is that you can always decompose a circuit into these products of local operators. The thing is just you don't know the support of these local operators.
Right.
But even that's the case, you can still learn these local operators from classical shadows just by a quantum analog of classical Honta learning. Yeah.
Hi, Yunchao. Thanks for the nice talk. And you mentioned that your algorithm also works for polylog depth unitary. So is there any modification needed? Because in that case, the light cone are much bigger.
Yeah, so I claim it was in quasi-polynomial time, just because the light cone is much bigger.
Okay, so then what stops it from being generalized to like Permian depth circuit?
And then it's exponential time.
Okay.
Yeah. Dominic.
Thanks for the talk. How do your algorithms compare to MPS and MPO tomography? It seems like very related, and maybe you could generalize them to PEPS tomography.
I'm not really sure about PEPS, but indeed MPS and MPO solves the problem in 1D. The reason that we really care about higher dimension is because 1D quantum circuits are classically easy.
Right, but how do I guess my question is how your algorithms compare to these algorithms?
Oh, I would say it shares some similar spirit because some of the MPS algorithm also has a disentangling algorithm.
Thanks for the talk. I think I missed a maybe super basic point. So how do you learn this like local inversion unitary like V1 and V2?
Right. So maybe the simplest way to see that is that maybe you can just do local tomography to learn a local channel, and then you can classically search for all small circuits, and you just apply it to your tomography result, and then see if some of the wires are disentangled. This is something you can do in classical post-processing on top of the classical shadows.
I don't see any further questions at this stage. And let's thank Yunchao and all morning session speakers again. And we will be reconvening at 2 o'clock.